This talk is dedicated to Father Peter Rinaldi, a man who spent over 70 years of his life dedicated to the Shroud of Turin. I only knew Peter It was my pleasure to only know Peter, let me amend that, for about 10, 12 years. Over that entire period, he expressed nothing but constant concern over the problem of the conservation and the preservation of the Shroud. At the Hong Kong expedition, which I was fortunate enough, or maybe unfortunate enough, to be involved with, you can ask Rex Morgan about that, Peter made what I think is one of the most moving statements about the Shroud of Turin at the end of a small talk he gave on his involvement with it. It's worth everybody listening to. Peter made the point that his faith did not depend on the scientific analysis of this cloth. Rather, what he felt about the analysis of this cloth depended upon his faith. Peter is not the only person who has that viewpoint. There are millions of people out there who don't care two bits about what those of us of science have concluded or not concluded about the Shroud of Turin. To them, this is a symbol of their faith, and they only want to know one thing from scientists. What are you doing to protect this image? For those people, the very best that those of us who have been involved with the scientific studies in this shroud should be devoted to answering that question. Therefore, in this talk, I am not going to bother to be concerned with all these extraneous issues about authenticity. I'm not going to bother with the mass media miscoverage of some of these things. I'm not going to try to tell you how people have misused the scientific results. I'm going to tell you instead about the problems involved in conserving and preserving this image. The first thing I have to tell you as a scientist is nothing lasts forever. Mountains wear down, valleys deepen, and even man-made objects suffer this. Some of you may know Percy Bysshe Shelley's poem about Ozymandias, King of Kings. The same is true of the shroud. It is made out of matter. It will, over a period of time, degrade. Point number one, we're not interested in just preserving the cloth. The issues of conservation go far beyond that. The people who are interested in this cloth are interested in preserving and conserving the images on this cloth. Those are two different things. The first thing to recognize is you cannot conserve an unknown chemical structure. You must know what the chemistry of the materials are that you're trying to conserve. That has lots of consequences. You're all aware there are vast polemics as to what the chromophores are. They can be summed up quite readily. There is one person who's one of the world's leading microscopists, Dr. Walter McCrone, who says this is nothing but ink. It's nothing but iron oxide suspended in a protein binder, painted upon the surface of this cloth, and to make the blood look better, some mercuric oxide or cinnabar has been mixed up with it to give it a red color. Period. You might think of this as the adherent chemical theory. What we're talking about is somebody applying material to the surface of the cloth. So you've got a binder, you've got some pigments in it, and it's their chemistry we're concerned with. The chemistry of the binder, the chemistry of the pigments. In opposition to that is the work that I myself have been involved with my colleagues in STIR, putting together all the chemical studies that John Heller and I did, all the studies that I've done on my own, all the spectroscopic work that's been done by my colleagues in STIR. We advanced a very different theory for the colors, the chromophores found on the surface of the shroud. First of all, we claim that the image is nothing but the fact that it a large series of chemical reactions on the cellulose surface of the fibers comprising the weave of the cloth itself. A series of dehydrative oxidative reactions, the same type that happens when linen goods go to pot in your own kitchen, your own dining room, and the rest. Linens, as you know, yellow. That is the color that gives the image that we see on the Shroud of Turin. The blood, we claim, is actually blood-derived material. And there's something that must be specified here. There are too many people that think of the blood on the Shroud as whole blood. It took a long series of experiments by myself and some also by Dr. Lavoie here in the audience to finally arrive at the very interesting conclusion that, in fact, the blood that we see on the Shroud is an exudate from clotted blood. Vignon was the first to point out that the blood images we see on the Shroud are clotted blood, which had never been represented that way, blood in classical artistry. That has a number of interesting consequences. One of the interesting ones is that the blood is red. There are no end of people that said, see how dumb the artist was, he painted the blood red. Everybody knows that blood turns brown with time as a thin film, or black. It's found in large amounts like in mummy material. The reason why the blood is red is because this is a man who suffered a traumatic death. Because of that, many of his red blood cells lysed. They went through the liver. Hemoxygenase converted a great deal of that to bilirubin. And this was squeezed out of the clot. So what you actually see there is, in fact, haptoglobin-bound hemoglobin in the met form, the parahemoglobin form, because it's dried out and suffered a protein conformation change, bound up with albumin, which contains a lot of bound bilirubin. The parahemoglobin form of hemoglobin is a brownish color. The protein-bound albumin is, in fact, an orange color. The combination of two gives you the red blood you see. We'll see later the fact that this is what the blood color comes from has a number of very severe consequences with respect to conservation. All right, what other problems do we have to worry about before we talk about conservation? Now some ideas what the materials are that are in the images. The next thing you have to know about conservation, you can't conserve an object unless you manage to assess what's happened to these materials. What do we know about assessing how much damage the Shroud has already suffered, both to the cloth, to the image, and to the blood? The answer is almost zilch. You heard my previous colleague, Maria, told you that she estimates that something the order of 40% of the blood has been, in fact, abraded from the surface of these fibers and lost. My own estimate is a little bit more conservative, 25 to 35, but I accept her 40 instantly. I like that number. There isn't a single tape that I've worked with samples from the Shroud, both Fry's and those that Sturp took, that does not show three things. Red silk in the backing cloth is pervasive over the whole cloth. Blood shards can be found everywhere, and charred fibers from the scorches. They're found ubiquitously over the entire surface of the Shroud, from the fact that it's been constantly rolled, folded, and redistributing this abraded material over the entire surface. It, of course, makes interpretation of what you see in the tapes very difficult. As you read our papers, realize we spent a lot of effort untangling some of the consequences of the fact these materials are found everywhere, plus a lot of junk, which we'll also have to speak about shortly. You not only need to assess what's happened, but if you're going to have a conservation program, you have to continuously assess it. Conservation is not a one-time thing. You don't get a bunch of experts in a room and say, listen, what should we do it, and it's done forever. You have to constantly monitor it, particularly something as complicated as the Shroud of Turin. Fortunately, there are available to us today a number of very advanced analytical techniques to allow us to monitor this in fact, non-destructive way. I should point out, unequivocally determining the nature of some of these chromophores might involve going back and actually taking some limited sample material from the Shroud again for the purpose of not doing simple on-site spectroscopy, but in fact some very intense analytical chemistry with specialized instruments. You cannot depend on the fact that I look like a nice guy and Walter McCrone doesn't. That doesn't suffice for deciding how you're going to base your conservation program. You have to know. There are a number of Fourier transform infrared methods that can be applied, UV visible techniques, some new advanced surface wave techniques using photoacoustic methods, and also some new types of surface electroanalytical techniques. Now, I stress the fact that these have to be done as surface techniques. And that might not be obvious to people, but it's easy to make measurements on the shroud and conclude junk if you don't stop and think about what you're doing. Some of you may be aware of the fact that one of the things we did in the STIRT testing was to take a transmission photograph. That is, the light source was placed behind the shroud, and then a photograph taken. When you do that, something quite remarkable happens. You can still see the water stains, you can still see the blood stains, but the image disappears. Why does the image disappear? Because the image is only 2 fibers thick on the surface of the shroud. The thickness of that image is less than the thickness of a human hair. Got that? So the image is only a human hair thick on the surface of the crowns of the thread of the upper surface of the shroud that shows the image. That's not the only problem. If you look at the discolored fibers themselves, you discover a number of interesting things, some of which I'm not going to go into because they're part of the arguments that this is not a painting. For example, it's not a pigment concentration image. It's what's known as an areal density image. All these fibers have exactly the same absorbance, only a few %, which also produces problems. But the other thing is, Walter McCrone would tell you it's a very thin painting on the surface of these fibers. And in fact, our results, by a completely different technique from his, show that whatever this chromophore is, it is very thin on the surface. And in fact, we use phase contrast microscopy to do this. We use Hoffman modulation. But we're free of diffraction artifacts. His is not. That's very important because it turns out this chromophore is only the order of a few tenths of a micron on the surface of the fiber. And what does that mean? It means that the amount of chromophore on the shroud is the order of 1 part per billion by weight. There's not a lot of chromophore there. So if you use a brainless technique for analyzing what's there, you won't see it. You have to use reflection spectroscopic techniques where you don't even know that it's there. And it has to be incorporated into your monitoring. Those pieces of equipment should be bought, should be put under a permanent monitoring program, and installed with the display or the storage characteristics, however the shroud's going to be kept. All right, those are the 3 basic problems. What are the physical, chemical, and biological factors that will lead to degradation? Here they all are. And some of them are not the usual things that people have considered. Let's start with the strongest type of energy interaction that can happen, ionizing radiation. Now, this could be ultraviolet light, it could be natural radioactivity, because these things are kept in stone buildings. It could be radon in the air, you know all about that. But I'm less worried about that than cosmic radiation. Right now, every person in this audience is receiving cosmic radiation and is producing damage to your tissues. But it isn't just cosmic radiation. There's an upper energy scale for cosmic radiation. There's some extremely energetic cosmic rays called Auger particles. These particles have enormous energies. The energy to break chemical bonds, the sort of things we're talking about on the shroud, ranges from about 80 kilocalories per mole to about 120 kilocalories per mole. 4 to 5 electron volts. The energy that's in Auger particles is in the giga electron volt range. This is in the range of billions of electron volts. So a few of these come down and hit the shroud. I might point out at one time it was in vogue to think of these things as producing senescence in living materials. When one of these things hits, it produces a lot of damage. It has a lot of energy. All right, so one of these things hits one space in the shroud, it breaks a few bonds, so what? Well, that's not the problem. We put this shroud in metal containers. That verges on the stupid. Why? Because when one of these Auger electrons hits a metal, it gives rise to something called secondary ionization. It produces material in the X-ray range. If you ever look at a picture of this, you see an incoming track, and on the other side it looks like a thunderstorm. There are literally millions of tracks. So Auger electrons aren't very frequent, but when they are frequent, they hit metal, they do a lot of damage to the shroud. That says, stay away from metals. There are some alternatives. You can put up a 9, 12-foot thick lead shield over it. If you ever have an earthquake, that'll be a disaster. It's also not very aesthetic. Or you can put the shroud in a salt mine a mile underground. I think you'll soon think that's not very aesthetic either. Most people are not going to troop a mile underground to see the Shroud of Turin. So that means that one of the first considerations we should do, if we don't want to deal with this problem, is in fact to avoid any metals in the immediate vicinity of the shroud. That means this new theory, we should roll it up, put it in a titanium cylinder, is no. Think about that. How long will it take for this damage to produce problems? Fortunately, millennia. So it's not something we have to worry about in a hurry, but one should be aware of the fact this should be assessed and something should be done about it. How about non-ionizing radiation? Well, this brings us down through the ultraviolet, where we see the same kinds of problems we've just spoken about with the ionizing radiation. The visible radiation. After all, we'd all like to see the shroud permanently displayed with the lights on it. We could all look at it. Is that a bright idea? No, it isn't. Why isn't it? It turns out that the energy degradation of the shroud, which I'll speak about in a moment, that is the cloth that's non-image, the activation energy for that is much lower than that for thermal processes. I'll speak about that in a moment. So leaving it in the light could in fact produce some pretty severe damage to the non-image areas, as well as damaging the image areas. But there's another very tricky thing. Remember I told you about the blood being red? Remember I told you it's because of bilirubin? Bilirubin is a very good photochemical material. When you talk about people who have jaundice, excess bilirubin, you know they're photosensitive. Some may know about the problem of bronze babies. You also know that the therapy for it is phototherapy. You put those babies under blue light, the bilirubin undergoes a reaction, an isomeric change. It's worked out by a colleague of mine by the name of Anthony McDonough. In fact, I've spoken to about this whole problem with the blood. And it goes colorless. Well, that means if we put visible light on the blood, what's going to happen to the color? It's not going to stay red. How long will it take, and why hasn't it gone red already? The reason it hasn't gone red already is because most of the time the shroud's been kept in the dark, and furthermore, the hemoglobin that's there acts as a quencher for this reaction. But acting as a quencher doesn't stop it. Normally the bilirubin that's there would disappear, for example, in these kinds of lights on a shirt. Tony gives a talk with the structure. It disappears by the end of his talk. Something about half an hour to an hour. Under the quenching exposure to light, you might expect something in the order of maybe months to about something, maybe a year and a half. It'll go colorless. The blood's color will change. Is that something you want to entertain just so you can look at it? There's another problem. Some of these photoreactions that can take place on the shroud are what are called photosensitized. Draper's law says you can't get photochemistry unless the radiation is absorbed. This is a white cloth. That means all the light's being reflected. How do you get photochemistry? Because in the cloth we have a number of transition metals. There's iron bound to the cellulosic structure of this cloth and its degradation products over the entire surface of the cloth. It's a very good photosensitizer. You're not going to remove it. There's no way you can remove it without destroying the cloth. You might be able to shift it by binding it with something, but that would change the whole color of the cloth. You could put the cloth behind filters. That wouldn't be very aesthetic. I don't really think people would like looking at the Shroud of Turin through a great big film of red celluloid. So the photo issue is going to be a problem. Somebody's going to have to make a decision what you're going to do about it and how it's going to be dealt with. Museum kind of conditions of lighting could in fact do something I'm going to talk about in a moment when I talk about temperature. Instead of over millennia to years, they could produce the problems in months to weeks. Remember that. All right, let's talk about mechanical stress, humidity, and pressure, and a little bit about temperature. Their problems all fall in the same class, something called mechanical stress. If you take any material and you stress it by either pulling upon it, putting it under tension, or bending it, you produce surface catalysis. The rate of chemical reactions can go up as much as a factor of 100 to 1,000 under these conditions. Such surface catalysis is not unknown for fabrics. One of the fastest ways you can get a fabric to oxidize quickly is to bend it. It'll oxidize where it's bent very quickly. All right. What produces mechanical stress? Stretching, gravity. By the way, I should have told you one of the ways to avoid this problem with the ionizing radiation is to stop rolling the shroud up, which we want to do because of these problems of mechanical stress. Every time you roll it and fold it, abraded materials get abraded off, either Macron's pigment or our blood, as Maria's demonstrated to you. So you really shouldn't keep it rolled or folded. I don't care where you're going to display it or store it. You should store it in a long box, which is the shape of the shroud. That's the second conclusion. How do you place this? Well, if you want to avoid the cosmic radiation problem, you have to place it perpendicular to the Earth's surface and upright. Why? Because it makes the smallest target area. If you face it this way, you increase your target area by a factor of 4. If you put it this way, you increase your target area by a factor of several hundred. So you don't want to leave it face up and face down. Well, that's great from the photo problems. How about these mechanical stress problems? You put it this way, it's subject to a number of stress problems, including vibrations. What will they do? Well, over a period, all these adherent materials, like Dr. Macron's pigment or the blood, will be shaken off. Cellulose is interesting. The fiber does not stretch and swell isotropically. It's anisotropic. Any of you ever can't know that cellulosic tent ropes, cotton linen, swell much more radially than they do longitudinally. Every time the humidity changes, you get one of these microstress environments. Every time a truck goes by, you get one of these microstress environments. Every time there's a tidal change due to the moon, we get some of these stress effects. Every time there are pressure changes, you get some of these stress effects. Every time there are temperature changes, you get some of these stress effects. What's the net result of this? It'll take away all the abraded material over a certain amount of time. If Walter Macron's right, it's a painting, it'll take a little bit longer time. The blood is already coming off. It's too late for some of the blood. Something should have been done about that already. How about the idea of just putting it under a vacuum? Dumb. You take all the water out, you're going to have trouble. Cellulose oxidizes and degrades a lot faster under vacuum than it does under air. The water is necessary for the integrity of the structure. Furthermore, some of the chemistry we postulated requires dehydration. You want to speed the chemistry up? That's the way to do it. Dehydrate it. Put it under a vacuum. Temperature. Now we come to something very serious. If the image is what we postulate it to be, over a period of time, something very significant is going to happen. Right now we see a variation, we see an image, because something produced a variation in the extent of these chemical reactions that produced this oxidative process. In other words, it's been differentially oxidized. But this can happen to all the rest of the linen, including the non-image, that is exposed to oxidizing materials, oxygen in the air, plus some that are already on the cloth. Over a period of time, even at room temperature, they're going to undergo the same chemistry that produced the image. What will happen if that happens? Well, eventually, the image will be one solid silhouette without any definition of features. Furthermore, beyond that time, the cloth itself will come to the same intensity of background, because this is a saturated chemical reaction. Remember I told you every fiber had the same absorbance to a few percent. As the image, what will happen then? You'll have a uniform piece of cloth. It'll look yellowed with age, but there won't be any image on it. I don't think people would find that a very happy consequence. How long will it take for that to happen? Well, you can actually take literature data on the oxidation of cellulose. You need to use a few fancy equations. You need to use a half-time equation. You need to recognize this is a pseudo first-order molecular reaction. You have to recognize you're going to use the Arrhenius equation. And there's two adjustable parameters you have to pick. one on this type of reaction, and one for the energy it takes for this reaction to go. If you take a reasonable range of so-called Arrhenius 4 factors, 10 to the 20th to about 10 to the 21st, these range in the literature 10 to the 18th to 10 to the 26th, by the way. They don't apply to the types of reactions we're talking about. And you start plugging in different activation energies to discover something interesting, because this is exponential. We don't think exponentially, we think linearly. As you start lowering this activation energy, you find that reactions that take place the order of millennia suddenly start taking place in centuries, years, months, weeks, days, minutes, seconds, milliseconds, microseconds. Where in this range of things is the number that counts? The number that counts is somewhere between 30 and 35 kilocalories per mole. And the sort of chemistry we've done allows us to make an estimate. That's the rate at which thermal degradation has been taking place on this cloth. Well, that's great. For that kind of number, we could wait for image degradation for half a millennia to maybe a millennia and a half. There's a small problem. The problem arises by the fact that reactions can be catalyzed. Remember I talked about surface catalysis? There's also photocatalysis. This has activation energies of the order of 12 kilocalories. That means what's taking place in millennia for photoreactions can take place in weeks, months. Very dangerous. That's why the problem here with non-ionizing radiation is a serious one. What kind of things do we have to worry about that could catalyze the oxidation of the image further or the non-image? Sweat is a very good one, as any housewife will tell you. Salts, transition metals that are already there that can act as photosensitizers that are bound up in the cloth from a retting process. Air pollutants. You know, it's sort of interesting. The world's population density has gone up. Most people now live in urbanized conglomerates. Somewhere around 2/3, 3/4 of the people in the world live in cities. That's an interesting fact. When they live in those close concentrations and they have good living standards, they produce lots of air pollution. When they produce lots of air pollution, you can watch the rate of increase in art objects. People have noted steadily that art objects that used to be in museums and parks and buildings and all these things were stable for hundreds of years. In the last 20 to 30 years have started going to pot in a hurry because of air pollution. Does air get in and out of these containers? You bet it does. Is Turin an industrial city? Yes, it is. Has anybody ever monitored this to see what its problems are in the Shroud? No, they haven't. Should we start thinking about monitoring it? Yes, we better. Because that could drop this energy something in the order of 5 to 8 kilocalories. If you do that, anybody want to take a guess how long it could be before we see the Shroud go entirely? You know, one color? Try 20 years. So in fact, there are spectacularly stupid things that we could do if we don't pay attention to what some of the problems are. All right. If I haven't terrified you enough, there's another problem. There's all sorts of things people have talked about putting in contact with the Shroud. Plastics. I just told you about the problem of metal. You know, they're safe, they're good materials. I'm going to talk a bit about the biology in a moment. Let's put insecticides, rodenticides, all these things on it. There's all these things that are already on there on the cloth that are on there, the red silk and all the rest of it. What about those things? Every single one of those could act as a photosensitizer, as a catalyst. Isn't that interesting? If we're talking about the chromophore being a conjugated carbonyl, every single organic chemistry textbook that's ever been written has about 2 chapters on the chemistry of carbonyl groups. They're very reactive. They react with amines, they react with aldehydes, they react with ketones, they react with alcohols, they react with all kinds of interesting things. Since conjugated, the reactivity is potentiated. In fact, many of these things you react them with it, they produce colored products. Wouldn't it be nice for somebody to throw in this nice material that has an amine on it that makes a shift base, and it will get rid of all the bugs that are on the Shroud. The next time we come back, you open it up and the image is turned blue. Could it happen? You bet it could, because people are not thinking about these kinds of problems. If I haven't terrified them enough, let's talk about the biology. Fry looked at pollens. Giovanni Ricci did, and he discovered there are some mites there. We know nothing about the microbiology of the Shroud. Can we assume it's like other cloths? No, you can't. My colleague, Dr.
Garcia Valdez is going to tell you about some interesting fungi he's finding on Shroud material. We don't know what's there. Fortunately, the mites that Rigi found aren't the type to chew up cellulose. There are some that are there. Is there things that could happen we wouldn't be happy about? You bet. There's something called obligate anaerobes. These are materials, bugs rather, microorganisms, that do not require oxygen. And in fact, oxygen poisons them and inhibits their growth. However, they lie around waiting for somebody to be stupid enough to take the oxygen away. When you take the oxygen away, there's no longer any competition, they start growing. What's the first thing they're going to attack? They would just love degraded cellulose. Cellulose is nothing but sugar. It's a polyglucose. All organisms love sugar. You all love sugar. It's one of the things that's wrong with our civilization. We're all taking too much sugar. That's where most of your cholesterol problems are coming from. It would be pretty stupid to put the shroud under a vacuum and discover that way there are obligate anaerobes there. Somebody better start doing a microbiological survey of the shroud before people do something that's not very happy. Are there miscellaneous problems to deal with? There's lots of them. I really only touched the surface in telling you about some of these kinds of problems. There's a lot of debris on the shroud. One of the banes of my existence was to examine these sample tapes. You can find everything in the world on those sample tapes that's ever been in the vicinity of the shroud. There's small pieces of glass, there's gilt fibers, there's umber, there's artist pigments, there's pollens, there's flies' wings, there's hairs from animals, there's certainly dog hairs. There seems to be some other strange primate hair. There's synthetic, fibers on it. Everybody who's heard me talk before, one of the things we detected is something that looks like spandex, pantyhose. You can think strange things, but it probably came from a glove. Everybody who's ever touched the shroud with gloves has probably done more damage to the shroud than people who've touched it with their bare hands. Isn't that an interesting fact to think about? In fact, there's a very simple rule here with respect to talking about applying any type of chemical material to the shroud. If you can smell it, don't put it near it. That's what rules out plastics and all these various types of sides that we've talked about putting in. Until we know what's going on. Should you take all this debris off? Paul Maloney is going to give you an interesting argument. This would be a mistake. There's a lot of historic information involved in that debris that's there. Father Fossati, whose talk you heard Dorothy read you, will point out something interesting, which was first made obvious to me in New London by Ian. All these artist pigments that some people include as proof that an artist made it are only proof that an artist copied it. Because many of these early artists took their copies and sanctified them by pressing them on the shroud. Father Fossati has studied a number of those. In fact, just as an interesting aside, analyzing those could in fact allow us to fill out some of the art history of copies. Spectroscopy today could allow you to relate some of those materials when they're mixtures to specific sets of artists and specific sets of artist pigments. We finally come to something else, some things that should be classed what you might call acts of God. Earthquakes, severe storms, floods, and something which has happened to Shroud at least once before, and we think maybe twice before, fires. We know there was one at Chambéry, and a lot of people have postulated there's another one at a previous time that may account for the poker holes. By the way, those are not poker holes. If any of you are interested, the so-called famous myth that Philip the Duke of Anjou took it to Vienna, boiled it in oil, and then tested it with a hot poker is nonsense. If that had happened, whether you believe Walter's right or I'm right, the blood would have turned black. Since it didn't, it was not boiled in oil, and those holes were not made with a poker. They're surrounded by wax. That produces other problems we should think about. What should you do about that? Should you leave it there? Should you take it away? What will it do? So there's all the standard things. The thing I told you about earthquakes says you shouldn't put this 9-foot thick lead thing above it. We still have a problem that I've told you it shouldn't be folded, should be kept in some rectangular shaped material. It should be kept under some hermetic atmosphere so we can avoid all these pressure, temperature, humidity changes, but I told you there's a problem. What atmosphere you keep it under? It may turn out the best thing to keep it under is air. There's a limited amount of oxygen there. There's already materials on the shroud that will continue the oxidation and the scorches, by the way, even if you take the air away. And finally, there's another form of protection that we must worry about. You're all aware of the fact today that there's something called vandalism and terrorism. Could this happen to the shroud? Sure it could. Gee, I didn't expect it to be that startling. This gentleman just dropped it when I mentioned it. We should really provide for that sort of thing in talking about display and storage conditions. How do you stop somebody from throwing a bomb in or doing something stupid with it? All right. You all know the famous homily, the best laid plans of mice and men have to go astray. With all of these things about protection, if we can work them out, something could still happen to it that we don't anticipate. You could have a big storm or a hurricane that destroys wherever it's kept and destroys it. We should have been archiving this 10 years ago. The very best forms of photographic storage and various types of computer scanning storage should be applied to this cloth as soon as possible, and it should be thoroughly archived for lots of reasons. Not only to make sure this image exists for as long as the human race does, so that believers could look at it, but so in fact investigators like yourself could have questions answered without going directly to the shroud. You could go to this archival material and to look at these things if it were done properly. All right, we've learned this thing isn't trivial. It's not something that's going to happen by getting a group of experts together once, making a quick decision and saying this is what you're going to do. It's going to require a lot of further study to assess what's there and what's going on. And when you've done that, it's going to further require a lot of original research to learn how to do what we want to do. No one in the history of man has ever conserved blood on an image of this sort. Furthermore, no one in history has ever conserved the type of blood that we claim is there. This is even more serious. It's going to be an original research problem to figure out how to do this. When you're done, someone is going to have to sit down and make a risk-benefit analysis, because you can't have everything for nothing. If you're going to protect something some way, you're going to have to realize some other things are going to go. If you want people to look at it, you better start thinking about the fact that blood's not going to stay red. But in fact, it's worse than that. How long do we have? You'll be glad to know this is my last acetate, my last act of terrorism. All right. As I've told you, we really have millennia before we have to worry about serious problems of the degradation of the cloth itself, unless somebody does something spectacularly stupid. I think I've tried to convince you there are a lot of things people could do that in fact would be spectacularly stupid, and in fact have been entertained, unfortunately. All right, how about the image itself? There, we have to worry about whether you think of this as a painting or our theory that it's in fact a conjugated carbonyl as the poem. If it's a conjugated carbonyl, again, if people do some things and don't do something spectacularly stupid, it's good for half a millennia to a millennium before we have to worry about serious degradation of the image. However, if we don't start worrying about air pollution and don't start monitoring it, as I tell you, this could happen in as short a time as 2 decades, as 20 years. Serious problems. Nobody knows when it's going to happen or not. Nobody knows whether that image has been getting darker with time or lighter with time. It's just, in fact, an historic fact that we don't know anything about. Where's the serious problem? It's the blood. My colleague told you the blood is already being abraded away. I've told you it's found ubiquitously over the surface. It's going to get worse because as it begins to abrade away, it gets easier and easier to keep abrading it. The rate accelerates. It isn't linear. It's one of those exponential things I tell you people don't understand. How long have we got? Some of you may bring some of your children or grandchildren to see the Shroud if it's put out on exhibit after the turn of the century. If you want my guess, you're going to show them that's where the blood used to be. Will it produce other problems in itself besides turning brown or wearing away? Yeah, because one of the interesting things I did was to take the blood off some of the blood-coated fibers, and guess what? It looks like the non-image area. So we now see blood will look like something that's the opposite color to what's there now. This could be serious damage to the aesthetic value of the shroud. There are all sorts of things we could do. We could put this thing under cryogenic storage in a salt mine in an area that's elevated so we don't have to worry about floods, in something that's earthquake stable, in solid granite so we don't have to worry about thunderstorms and the rest of it, and only allow people to see televised images of it that we take in the infrared and then convert back to the visible. That would protect the shroud forever from all of these things I've talked about. It would be extremely expensive. We couldn't predict it would solve all the problems, but we still haven't investigated the microbiological problems. They might thrive then. But on top of that, it would not be aesthetic. I point out to you that the major problem in the shroud today, and I hate to tell you this, or maybe I'd love to tell you this, is not its authenticity. If we don't start making people aware of the fact that it's got to start being conserved and preserved now, you won't have any image to talk about it to have authenticity. It will be gone, and there won't be anything to talk about the authenticity of. So I urge you, take the things I've discussed in this talk very seriously and make sure people realize that the thing the news media should be talking about, and the things that scientists should be talking about, and the things that historians should be worrying about is in fact the conservation and preservation of this cloth. If we take care of that, then all the other problems will eventually resolve themselves. Thank you.